Hello, my name is David Murray. I'm the Associate Director for Prevention and the Director of the Office of Disease Prevention at NIH. Let me welcome you to the NIH Office of Disease Prevention's Mind the Gap webinar series. This series explores research design, measurement, intervention, data analysis, and other methods of interest to prevention science. Our goal is to engage the prevention research community in thought-provoking discussions to promote the use of the best available methods and to support the development of better methods. Before we begin, I have some housekeeping items. You can submit questions during the webinar via the chat pod. You'll need to open the pod by hovering your cursor at the bottom of the Zoom window and then clicking on the chat icon. Please direct your questions to hosts and panelists. We will open the floor to questions that have been submitted via the Zoom chat pod at the conclusion of today's talk. The slides and video recording will be posted on our website, prevention.nih.gov/mindthegap, in approximately 2 weeks. Lastly, we would appreciate your feedback about today's webinar. Upon closing, you'll be asked to complete an evaluation. We would appreciate your feedback as it will help us improve the webinar series. Today's speaker is Dr. Jonathan Moyer. Dr. Moyer is a statistician focusing on efforts to enhance the rigor and reproducibility of NIH-funded prevention research by promoting the use of the best available research methods. This includes expanding the resources available on NIH's Research Methods Resources website, providing guidance on the Methods Mind the Gap webinar series, and collaborating with NIH institutes and centers on projects that involve group randomization or delivery of interventions to groups. Dr. Moyer completed work on his PhD in biostatistics from the University of Massachusetts in 2021. His doctoral research focused on methods for group randomized trials. It's my pleasure to welcome Dr. Moyer.
Thank you very much, Dr. Murray. Thank you for having me. This presentation is based on a simulation study that Dr. Murray, our colleague Patrick Hagerty, and I published last year. So it's great to have an opportunity to present on this work. As a brief outline of the talk, I'll first review some concepts on multiple period group randomized trials, as well as outline some previous work in this area. Then I'll review the methods that we employed for the simulation study, including discussing its aims, data generating mechanisms, the target of the study and performance metrics, and the analytic models used. And then after presenting the results, I'll offer some discussion, and we should have plenty of time for questions at the end. Before I begin, I do want to note that the views expressed in this presentation are my own and don't necessarily reflect the position or policy of the NIH or US government. Group randomized trials are the focus of this work, and these trials are those that randomly assign groups of individuals to intervention conditions. This contrasts with individually randomized trials, which have individuals themselves be randomly assigned to conditions. Here's a simple diagram of a group randomized trial. On the left, before randomization, we have several groups or clusters, each represented with a different color. In this diagram, the groups look like small houses, but they could be anything. They could be schools, work sites, communities. Each group has several members participating in the trial, such that the participants are fully nested within group. The groups are then randomly assigned to either the intervention or control conditions, and all trial participants receive the condition to which their group is assigned. There are many challenges associated with group randomized trials. For example, outcome measures within groups are likely to be correlated because participants within the groups will have similarities. Ignoring this correlation in analytic models or power analysis may inflate type 1 error rates and result in reduced power. In addition, group randomized trials tend to have a small number of groups or clusters, usually less than 40, much less than 40, so there are limited degrees of freedom available for hypothesis tests. And group randomized trials tend to be more complicated to design, implement, and analyze than an individually randomized trial. They can have complex correlation structures and potential for bias to arise as the trial proceeds. So group randomized trials should only be conducted when necessary. And when might that be? One possibility is if the intervention operates at a group level. In that case, it needs to be a group randomized trial. There might also be some manipulation of the physical or social environment in which the participant interacts, perhaps signs at a work site or in a community. Group randomized trial might be useful then. And finally, a major concern, and one of the main reasons for group randomized trials, is that there might be a fear that the intervention can't be delivered without substantial risk of contamination. Multiple period group randomized trials allow for several different design configurations. This is an example of a 4-period parallel group randomized trial in which separate but parallel conditions are present throughout the trial, and there's no crossover of groups to intervention or control. Another example is a crossover group randomized trial, and here groups are randomly assigned to the intervention or control condition, but switch status at least once during the course of the trial. This diagram is another 4-period crossover group randomized trial, and here the groups experience the intervention condition twice. Because every group is observed under both control and intervention conditions, crossover group randomized trials tend to be statistically efficient. However, because the intervention is given and withdrawn, these designs are best used to evaluate interventions focusing on chronic or stable conditions, those that are unlikely to be actually cured or substantially altered by the intervention. In addition, another complexity with these trials is that there can be carryover effects that, in which the intervention effect lingers after the intervention is withdrawn. Addressing this might require lengthy washout periods. Another multiple period group randomized trial is the step wedge group randomized trial. And here groups are randomized to sequences, and the sequences cross over to the intervention condition in staggered steps until all groups eventually receive the intervention. Here's a 4-period step wedge group trial diagram. This step wedge trial has 3 sequences, and each sequence has 2 groups. While the step wedge design has received a great deal of interest over the years, especially in recent years, they're especially difficult to design and implement. They usually require specification of complex correlation structures, and it can be difficult to keep groups on schedule. For example, a group may decide to transition to the intervention condition early, or they may delay the transition. And in both cases will be threats to internal validity. And step wedge trials are also very sensitive to external events that can alter the implementation of the trial. So use of the step wedge trial should have very strong justification. The reference I cite below has by Hemming and Talliard has a good list of non-exhaustive justifications. One possible justification is that the staggered delivery of the intervention is the only logistically feasible design. Another justification might be that the step wedge design provides a randomized trial when the only alternative is a staggered non-randomized trial, and stakeholders can be convinced to randomly assign treatment order. So I shared some information about the crossover and step wedge group randomized trials to illustrate the variety of multiple period designs that are possible. However, those trials have a number of complexities that are beyond the scope of today's talk, so my focus will be on the parallel group randomized trial. Multiple period group randomized trials can also be classified according to the presence of repeated observations. In a cross-sectional group randomized trial, different individuals from each group are observed at each period. An example is from the Minnesota Heart Health Program, in which case 6 communities, each consisting of roughly 300 to 500 individuals, were surveyed at regular time periods on a variety of health incomes, but at each time period, there were new individuals that were observed. A closed cohort trial is one in which the same individuals are observed at each period. An example here is the Teens Eating and Nutrition study. In this case, 16 schools were followed over time to assess an intervention to improve nutrition among 7th and 8th graders, and it was the same individuals that were followed for these 2 years. When specifying analytic models for multiple period group randomized trials, there's several decisions that need to be made for the primary analysis. In this design, both individuals and groups may be followed longitudinally, so both require appropriate longitudinal correlational models. And particularly key for this presentation are representing time in the mean model as categorical or continuous, the specification of random effects for the model to generate. We can have longitudinal correlations within an individual as a result of these, or induced by these random effects. We can also have correlations among individuals from the same group. Finally, a third important choice is the choice of a covariance matrix for any random effects. We can represent time as a continuous variable using the random coefficients analytic model. Here, time is represented as continuous in group-specific mean models. Random effects that are used to induce correlation among the repeated observations amongst those who share the same group or member-specific trajectory. And they're interpreted as random slopes or group or member level deviations from arm-specific intercepts and slopes. And while the focus of my talk will be mostly on lines, first-order terms, that polynomial terms are possible in the random coefficient setting, but we won't explore that in this work. Here's a picture illustrating the random coefficients approach for a 4-period closed cohort trial. To simplify the presentation, I only show observations for individuals in one group, but hopefully it still conveys a general idea. On the x-axis, we have the time period, and on the y-axis, we have the outcome measure. The points having different shapes and colors represent outcome measures on individuals at the given time period. The black line represents the average trend of the group, while the other lines represent the average trends for participants. So note how the individuals have y-intercepts that deviate from the overall group y-intercept, as well as slopes that deviate from the overall group slope. These correspond, or these deviations from the group trend are essentially the random effects. And of course, I only show results for one group to simplify the presentation, so I only have one black line. If I generated results for another group in another arm, I could plot them here and have another group trend. And then in addition, I could show the overall trend for that particular arm. The other way to represent, or another way to represent time is as a categorical variable using time-specific indicators, and we call this the repeated measures ANOVA setting. Here, the random effects represent group or member level deviations from time-specific arm means. There are multiple approaches to modeling the covariance in this setting. We could have a simple random intercept model having only time invariant random effects. An exchangeable model is possible that allows for both time invariant and time varying random effects. Finally, we could have an unstructured covariance model that allows to be used for repeated measures on an individual. Repeated measures ANOVA model that specifies only time varying random effects, we call that a saturated model. So this name was chosen because a consequence of using unstructured covariance and time varying random effects is that as many within and between period variance covariance parameters are estimated as this. Here's a picture of the same data set that I used previously, but analyzed assuming categorical time. Absent are the trends, as we don't model those in this setting. The black dots here represent group means at each time period, and the random effects now represent member-level deviations from the group period means. Some of the first work in comparing these two approaches was done by Dr. Murray, based on the Minnesota Heart Health Program project I mentioned earlier. Murray et al. Murray and others in '98 compared the performance of random coefficients and repeated measures ANOVA cross-sectional parallel GRTs. They were particularly interested in preserving type 1 error rates for the null hypothesis of no differential trend. That is the interaction between condition and time. So they simulated data sets assuming these two mechanisms. For the random coefficients analytic model, they employed unstructured covariance structure, while for the repeated measures ANOVA analytic model, they used variance components structure. They found that the random coefficients analytic model maintained nominal type 1 error rate when applied to random coefficients and repeated measures ANOVA data. For the repeated measures ANOVA analytic models, nominal type 1 error rates were maintained when applied to repeated measures ANOVA analytic data. However, when these models were applied to random coefficients data, they exhibited inflated type 1 error rates. So as a result, the random coefficients analytic model, performing well in both cases, was recommended for use in general for multiple period group randomized trials. So since then, there haven't been many publications that have compared these two approaches. To give some flavor, Keza and Forbes investigated the impact of misspecifying correlation structures in the repeated measures ANOVA analytic setting. For example, they assumed one possible misspecification would be assuming correlation between outcomes within the same group at different time periods is the same, but it decays as a function of time. In their work, they didn't specifically investigate random coefficients in analytic models, but noted that further work was required in this area. Bell et al. In 2019 did some work with random coefficients models. They found that omitting random slopes in analytic models when such variation exists in the data generating mechanism results in standard error estimates that are too small. Bell and Rabe in 2020 published a simulation study in which they applied the mixed model for repeated measures to multiple period cohort parallel GRTs. In the context of the terminology I'm using, this is a repeated measures ANOVA analytic model with a random effect for group, no time by group random effect, and unstructured covariance at the member level. Bell and Rabe generated data sets assuming the repeated measures ANOVA mechanism with and without the time by group component of variation. And they found their main interest was on the intervention effect for the final time period. They found that nominal type 1 error rates when applying their analytic model to data with no time by group variation. However, they observed inflated type 1 error rates when applying their analytic model to data with time by group variation. So 3 key questions inform the aims for the current work of this simulation study. First, would Murray et al. Have found better performance with repeated measures ANOVA analytic models that use the unstructured covariance for cross-sectional data? So they used variance components covariance, and that makes fairly strong assumptions about the independence of random effects, while the unstructured covariance matrix doesn't. Second, would Murray have seen patterns in cohort data similar to those that they saw with cross-sectional data? Cohort data has a more complex covariance structure than cross-sectional data does. And finally, how important is the time by group random effect term in the analytic model if the data generation mechanism also includes variability at that level? Murray et al. Didn't investigate the impact of omitting this term. So move to the data generating mechanisms. Here's a linear mixed model representing the repeated measures ANOVA data generating mechanism. Linear mixed models represent or use both fixed effects and random effects to generate an outcome. The fixed effects represent the population level values and describe the association between the predictor variable and the outcome. Usually the fixed effects or some contrast of fixed effects are what's most of most interest in a GRT. And random effects represent random deviations from associations described by fixed effects. So for the cross-sectional and cohort data, we have these two data generating mechanisms. We have a continuous outcome Y. We have fixed effects for the condition, for time, and then the time by condition interaction. In bold, we also have terms for the random effects. The cohort version of the data generating mechanism also include, we have, so the cross-sectional mechanism has random effect for group, random effect for time by group. That's the same in the cohort version, but we also add a random effect, a random intercept for member as well. And the random effects are distributed as independent random normal variables according to these distributions. So if you're used to expressing regression models using notation with betas and x's, this notation may be unfamiliar. I could rewrite in terms of the other notation. For example, mu in these analytic models is usually the y-intercept or usually represented as beta 0. I use this notation mainly to be consistent with Murray et al. 1998. But I do want to note, because it's a common source of confusion, the terms TG and TC, they look like they might be products, but those are actually intended to represent a single quantity. And this TC is, again, the time by condition interaction, and TG is the time by group random intercept. Here are equations for the random coefficients data generating mechanisms. Some of the terms have similar definitions as the previous slide, so I've omitted them here. Now we have because time is continuous, we have a factor Tj, which is the time value of the jth period. I've added the LIN subscript to some of the T's to indicate that this is the interpretation of these effects should be in terms of a continuous time. And so TLIN represents the fixed effect for slope of the time trend in the control condition. TLING represents the random slope for a group. The cross-sectional version of this data generating mechanism has random intercepts for and slopes only for groups, whereas the cohort model adds a random intercept for both and slope for member. The interclass correlation, or ICC, is a commonly used measure to quantify within group correlation. It's in the RM ANOVA setting, it's very straightforward to define the ICC. So here are the ICC definitions for cross-sectional and cohort data. It's essentially the sum of the group level components of variation over the total variation. The random coefficients setting, we can also express an ICC. However, it's a non-constant function of time. So to simplify the presentation of results, I just used the repeated measures ANOVA definition of ICC throughout. We can also characterize the between period correlations at the group and member level using autocorrelations. The cluster level autocorrelation, or the cluster autocorrelation, is the overtime correlation of the outcome variable at the group level, and the individual autocorrelation is the overtime correlation of the outcome variable at the level of the member. This correlation will only be present with cohort data. So we undertook our simulation study by generating cross-sectional cohort data for both of these settings. For all simulations, there were 2 conditions, 5 equally spaced time periods, and 40 members per group. We specified 10, 20, and 40 groups per condition. All fixed effects parameters were set to 0, and we chose the random effects variances so that we had ICCs of 0.1, 0.01, and 0.001 under the repeated measures ANOVA definition. We also made choices of random effects variances so that we had a cluster autocorrelation of 0.5 and an individual autocorrelation of 0.7. And for each data structure, group per condition value, ICC and ICC value, we generated 1,000 replications. Our interest, in terms of the target and performance metric, our interest in this work was the differential change over time. That is the time by condition fixed effect interaction. Our target was the null hypothesis of no fixed effect time by condition interaction. It's important to note that this is different depending on how time is parameterized. In the repeated measures ANOVA setting, time is represented as a categorical variable. So for this approach, the null hypothesis is that there's no difference in the pattern of condition means over time between the intervention and control conditions. For the random coefficients analytic model, time is represented as a continuous variable. So the null hypothesis in this case, is that there's no difference in linear slope between intervention and control condition. And our performance metric is the type 1 error rate. And we did this for found it as the average for each of the 1,000 repetitions for each configuration. So having discussed the data generating mechanisms, we can turn to the analytic models. So on this slide, I've outlined the general linear mixed model. If you're not accustomed to matrix representations of linear models, this may seem abstract, but mainly I want to focus on the vectors gamma I and epsilon I, which contain the random effect and residual errors, respectively. When fitting analytic models, we can choose how to specify how these random values covary, and this is done by specifying the structure of their respective covariance matrices, G and R. So one possible structure is the variance components, or a structure. So here there is an independent variance component for each random term. As an example, here's the general form of a G matrix for one group for the cross-sectional repeated measure ANOVA data generating model. This is model 1 that we described earlier, and there are 5 time periods. The elements along the diagonal are the variances of the random effects. In this case, there are 6. The first is diagonal element in the top left is the variance for the group effect. This is the time invariant group random effect. The remaining diagonal elements correspond to variances for the time by group random effects at each period. So the second diagonal element is the variance for the first time period. And then moving on down the diagonal to the bottom right is the variance for the final time period. The variance for the time by group random effect at the final time period. The off-diagonal elements of this matrix represent covariance between random effects, and because the off-diagonal elements are all 0, the random effects are not correlated. Another common covariance structure is the compound symmetric structure. In this case, it's assumed that random effects have the same variance at each time period and a constant covariance. So in this example, this is a compound symmetric R matrix for an individual in a cohort repeated measures ANOVA. This is model 2, also having 5 time periods. In this case, the R matrix is 5 by 5 because there are 5 residual errors obtained for individuals. Unlike the previous matrix, the off-diagonal elements are non-zero, so there's correlation among the individual outcome measures. And in this case, it corresponds to the sigma m squared, which is the member level variance. A third possibility for is the unstructured covariance matrix. In this case, there are separate variances estimated for each random effect or residual, depending on if it's being used in the GRR covariance matrix. And separate covariances are assumed for pairs of random effects or residuals. This is a very flexible structure that makes no assumptions about the variance and covariance values. Finally, SAS also allows the specification of an unstructured covariance matrix called UN1. So this is a covariance matrix in which there are separate variances for each random effect, but the random effects have no covariance. This structure might be useful if you have the R matrix for a cross-sectional analysis in which you want to specify separate residual variances at each time period. The covariances being 0 in this case imply no residual level correlation across time periods, as would be the case with cross-sectional data. So armed with this knowledge, we fit 4 analytic models to each data set. And all analytic models contain fixed effects for time, condition, and their interaction. The first model is we'll call the repeated measures ANOVA with variance components covariance model. So here we specified random effects for group and time by group in both cross-sectional and cohort cases. In the cross-sectional case, the G matrix was specified as variance components. For cohort data, the G matrix was specified as variance components as well, and the R matrix was specified as compound symmetric. So the cross-sectional model 1A here was the approach that was studied by Moyer et al. In 1998. And 1B, we chose this because it will help us address AIM2. If Moyer et al. Applied this model to cohort data, would they have seen similar patterns as with cross-sectional data? The second analytic model category that we looked at was the repeated measures ANOVA with unstructured covariance model. So again, we had random effects here for group and time by group in both cross-sectional and cohort data. In the cross-sectional case, the G matrix was specified as unstructured. And in the cohort setting, the G matrix was specified as variance components, and the R matrix was specified as unstructured. 2A was chosen to study because it would help us address AIM1, where we would want to see if there's better performance with repeated measures ANOVA analytic models if we used unstructured covariance on cross-sectional data. And 2B was inspired by Bell and Rabe. In this particular Bell and Rabe model, as I'll discuss in a few slides, so they did not apply the time by group random effect. I did want to mention, I overlooked this previously. I don't specify the R matrix in cross-sectional data. It's because at the R matrix is used for repeated observations, and so it's a natural fit for the cohort data set or data setting. Finally, the third analytic model that we investigated was the random coefficients analytic model. So for cross-sectional data, we specified random effects for group and time by group. And the G matrix was an unstructured matrix. In the cohort setting, we specified random effects for group, time by group, member and time by member. And so the G matrix in this setting is unstructured as well for all random effect specifications. So the R matrix, we did not specify it in this case as the member level random effects were explicitly modeled. We were not trying to investigate any correlation amongst the residuals. The model 3A, it was the random coefficients approach studied by Murray in 1998. And then 3B was used to address AIM2. Would Murray have seen similar patterns in cohort data as with cross-sectional data? Finally, the fourth analytic model that we investigated was the saturated analytic model. So this analytic model had specified only random effects for time by group in both cross-sectional and cohort settings. The G matrix was specified as unstructured, and the R matrix was that UN1 structure I described earlier. In the cohort setting, the G matrix was unstructured as well, and then the R matrix was fully unstructured. Again, saturated is chosen as the name because as a consequence of using the unstructured matrix and these time-varying random effects, as many within and between period variance covariance parameters are estimated as possible. So this model was not neither 4A or 4B was investigated by Murray in '98. This is actually the idea by our colleague Patrick Hagerty. So it's a very flexible model, makes the least amount of assumptions about the nature of the covariance structure. So to recap, we have the four main analytic models, each with a cross-sectional and cohort version, repeated measures ANOVA with variance components, repeated measures ANOVA with unstructured covariance, random coefficients, and the saturated analytic model. Skipped a bullet there. For the first bullet, these four analytic models are referred to as the time by group analytic models, because, as you recall, the data was generated assuming time by group variation was present. But we fit variations of these repeated measures ANOVA and random coefficients analytic models that omitted the time by group random effect. So these are referred to as the intercept only analytic models. And these were used to address our AIM3, how important is it to have time by group random effects term in the analytic model if the data generation mechanism also includes variability at that level. So we conducted we applied our analytic models using SAS-Proc mixed, the F-test of the null hypothesis of no fixed effect time by condition interaction. That's what we focused on. As you might recall, the F statistic has both numerator and denominator degrees of freedom. For linear mixed models, the F statistic is follows only an approximate F distribution. We have to estimate the denominator degrees of freedom. There are many ways to do this. In general, the differences seem to be fairly minimal if we have a very large sample size, so maybe on the order of 100 groups. But if we have a smaller sample size, the differences can be more serious, and that's usually the case with most group randomized trials. So we employed the Kenwood-Roger denominator degree of freedom option. It performs well in most cases. This approach takes into account the uncertainty of using sample covariance estimates as covariance parameters during the estimation process. The bottom line is that the Kenwood-Roger approach tends to estimate denominator degrees of freedom more conservatively than some other approaches might, such as the residual option in SAS And, excuse me, Murray, so the first Kenwood-Roger paper came out in 1997, and Murray 1998 came out, Murray et al. Published in 1998. But Murray et al. Had spent some time in review, so the Kenwood-Roger innovation wasn't available at that moment in time. So that is a difference compared to what Murray et al. Did. So here are some results for the analytic models that specify time by group random effects. To orient you to this slide, along the y-axis, we have the type 1 error rate. And along the x-axis, we have the within period ICC, as we defined previously for the repeated measures ANOVA setting. Each column of panels corresponds to a data generating mechanism. Each row of panels corresponds to one of the 3 groups per arm values. The time by group, focus on the 2 columns on the left first. So here we see the results for the analytic models applied to the repeated measures ANOVA data settings. And all the analytic models performed well in this setting. If we look at the rightmost column, this is the application of the analytic models to the cross-sectional random coefficients data. The repeated measures ANOVA with the variance components covariance structure exhibited inflated type 1 error rate when applied to the random coefficients cross-sectional data, unless the ICC was very low, whereas the other analytic models performed well. And finally, the random coefficients cohort column, we see that both repeated measures ANOVA analytic models showed inflated type 1 error rates, unless the ICC was low, but random coefficients and saturated analytic models performed well. This chart shows the results for the intercept-only analytic models. Again, the data was generated assuming a time by group component of variation, and these analytic models omit that. All analytic models show severe type 1 error rate inflation unless the ICC was low. So it's very important. So it's potential for serious type 1 error inflation if that is not included. So let's revisit the key questions that we described earlier. Would Murray et al. Have found better performance with repeated measures ANOVA analytic models using unstructured covariance for cross-sectional data? So both the repeated measures ANOVA analytic models perform well on repeated measures ANOVA analytic data, or repeated measures ANOVA data, excuse me. We found as we were doing this that it was very important with repeated measures ANOVA, the unstructured version, to use Kenwood-Roger degrees of freedom. If we use the between-within version, we had actually inflated type 1 error rates, but the Kenwood-Roger approach corrects that here. The repeated measures ANOVA with unstructured covariance perform well on random coefficients cross-sectional data, but the variance components version of the repeated measures ANOVA analytic model did not, unless the ICC was low. Random coefficients and saturated analytic models exhibited nominal type 1 error rates when applied to cross-sectional data in general. Would Murray et al. Have seen patterns in cohort data similar to those we saw with cross-sectional data? Here they saw that random coefficients and analytic models maintain nominal type 1 error rates in cohort data generated under both mechanisms. The repeated measures ANOVA analytic models perform well on repeated measures ANOVA analytic model, or cohort data, excuse me, but neither perform well on random coefficients cohort data unless the ICC was low, and the saturated analytic model did well in all cases. And finally, how important is the time by group random effect term in the analytic model if there is variability at that level in the data generation mechanism? It's quite important unless the ICC was very small. During the review process for the article, it was suggested that the analytic models be applied to data generated with a group random effect, but no time by group random effect. So it's sort of the opposite of what we did. So we did this, and we found there was really no impact on type 1 error rates if the time by group random effects were included. So recommended to use the time by group random effects in all cases because there might be a problem if it's omitted. Finally, in conclusion, random coefficients and saturated analytic models specifying the time by group component of variation maintained nominal type 1 error rate to all data sets, both cohort and cross-sectional in the parallel GRT design. So recommending, these two approaches are recommended for the use of analyzing multiple period GRTs, allowing investigators to choose their approach to modeling time. And if analytic models only specify group level random effects, there's potential for substantial type 1 error rate unless the ICC was low. So it's a good policy it seems, to always include time by group random effects in analytic models. And with that, I am ready to take some questions.
Thank you very much, Dr. Moyer. We have a number of questions from the audience, so let me get started. The first one, which I tried to answer in the chat box, would it be possible to obtain the SAS syntax for the various models that were listed? For those of us who work in SAS and learn best by example, that would be very helpful. And correct me if my answer was wrong, but I said that the SAS code was available for download as a supplemental file, and I gave them the DOI number to get to the paper.
Yep, that's correct. We included the code in supplementary material. So yeah, but certainly if there are any questions about the code, you feel free to reach out to me, and I'd be happy to answer them.
That's a good way to get a very busy inbox.
Yeah.
You focused a lot on categorical time versus continuous time, and your findings indicate that it's possible to protect the type 1 error rate with either of those schemes. Is there any advantage to categorical or continuous, any advantage to one over the other? Or is it really just up to the investigator to choose the one that they prefer?
So for me, I find the categorical nature, or the categorical approach appealing because it's essentially non-parametric. It doesn't assume any particular underlying trend, and so it's just appealing in that sense. And if we assume like a underlying trend, we want to have to justify that, and we might be incorrect in our assumption. Your previous work showed, of course, that there was potential if the repeated measures of analytic models were applied to data generated, with the underlying trend, that there was inflated type 1 error rate. But the saturated analytic model in this case offers an opportunity to kind of to essentially not worry about that, and just kind of get the best of both worlds for both, one, not make any assumptions of the underlying trend, and not suffer from inflated type 1 error rate.
Thank you. You reported on simulations that used a continuous outcome. Have you done simulations with dichotomous outcomes or count data? Because those are pretty common in public health. How might the results change?
Right. So yeah, exactly. Binary and count outcomes are common in public health. So some work has been done to kind of show that mischaracterizing the variance structure in those settings can produce biased results. So with the continuous outcome, all the various terms in the regression model are additive, but in the binary and count setting, it's multiplicative, and so the way the variances interact with the estimation of the estimation of outcomes. So if for some reason the variance is misspecified, then there can be a potential for bias. So there are continuous approximations, of course, for the binary outcomes. These rely on large sample assumptions, so they may not be as suitable for the small sample configurations that we looked at in this work. So it'd be an interesting question to have answered. I have not personally done simulations with those yet.
Yeah, we have a related question. Is it possible to generalize the saturated model to binary outcomes if you fit the model by maximum likelihood using adaptive quadrature and using only random effects, that is, no repeated statements? That's a rather technical question, but perhaps you have some thoughts there.
Something sounds like it's definitely worth a try. I haven't. I guess I don't have too many thoughts on that particular approach, but
okay. Are the random effects covariance structures that you described, because you did everything in SAS, are those easily fit in R?
So R, so I find, yeah, so the most common function, or at least for me, that I have most experience with in R is the Elmer function from the LME4 package. And so in that case, it's assumed to be unstructured by default. There are ways to kind of specify the correlation structure to maybe impose some more structure, but unstructured is the primary approach there. There is another function, LME, from the NLME package that allows for more specification of covariance structures.
A very much applied question. Are there sample size calculators that investigators can use to design studies that will use, for example, the saturated model or the random coefficients model, since those are the two that you are generally recommending in with this kind of design?
Right. Yeah. So there's I'm not too familiar with the for the saturated analytic model. Any approaches with that? Certainly, the NIH RMR, or Research Methods Resources website has a calculator that can calculate these, although that's actually for only 2 periods. The calculators that I use frequently to kind of make these estimates, I use the cluster RCT Shiny app that's produced by Hemming and others. I don't know if that actually has a way to specify for saturated analytic model.
So yeah, things for further investigation.
Right, right.
When might these models that you're recommending, the repeated or the saturated model and the random coefficients models, when did you have trouble with failing to converge with model fitting issues in the simulations? Under what circumstances, and I'm thinking how small would the study have to be, before you'd run into trouble with this? Or in other words, how large does the study have to be to avoid convergence problems?
Right. So I didn't, with the data sets that I simulated, I didn't notice. I hadn't not hardly any issues with it. It seemed to work well. Yeah, I think maybe if there was the simulations we did are a fairly ideal scenario. Of course, we assume like equal numbers of participants within each of the groups. It's a pretty ideal, optimistic ideal setting. So maybe if there's differences in the or variability at the of the group sizes, that could impact it. And then yeah, maybe if there's a few small number of groups, there might be limited information with which to estimate all the various covariance parameters. Yeah, I guess I don't have a good sense. I'd have to make some more tests, run some more simulations to see. During review, I know one reviewer asked for, how would our results be if we had only 5 groups per arm, and we decided, we basically said that, probably, because there's so much fewer groups, it'd probably be even worse essentially than the results we see with for 10 groups per arm. So, but it might be worth doing just to kind of assess, the performance.
What about other kinds of designs? You mentioned crossover designs. You mentioned step wedge designs at the beginning, but didn't include them in the work. Should we be thinking about variations on saturated models or random coefficient models for those kinds of designs? Is that just work that still needs to be done?
Yeah, it's a great question. I think there's a lot more work, still a great deal more work that can be done in that setting. I do know of some papers, I believe, that have investigated random coefficients approaches in step wedge. I would think the saturated analytic model would apply in for both crossover and step wedge designs in a fairly straightforward fashion. I don't see why it shouldn't perform well in those settings. In my experience, usually, certainly for step wedge trials, but even for crossover, it's categorical approaches to modeling time are popular. So I think, I think the saturated analytic model would be a good fit.
Do you have any sense of the relative power of the two approaches that you recommended? So I'm thinking the saturated model versus random coefficients. And I recognize that the answer might be, well, geez, if you've got data that really fits the random coefficients model, that model's going to do better in terms of power. And if you don't, the saturated model might do better in terms of power. Is that the answer, or is it more complicated?
Yeah, we didn't compare power for the two approaches. Certainly the random coefficients analytic model, so that assumes a linear slope with time, and if for some reason the true trend of the data or the true structure of the data is not that, that can result in reduced power. And yeah, like you say, we could assume higher order polynomial terms to maybe better reflect that association with time. But then again, we might never know the true underlying trend. So
I'm going to try to sneak in one last question.
Okay.
Have you considered comparing your best performing models from this simulation with GEEs that are robust to misspecification of the correlation structures, and what might the results look like?
Yeah, that'd be really interesting. I've actually I've thought of it. I just haven't sat down to actually do it. Definitely think that would warrant some investigation.
All right, Dr. Moyer, I want to thank you very much and for your excellent presentation. You're getting rave reviews in the chat box. I want to thank the audience as well for listening today and offering terrific questions, more questions than I can get to. On the Mind the Gap website, prevention.nih.gov/mindthegap, you'll find several resources for this talk, including the slides and a list of references. Those are available today. We will also post a recording of today's webinar on the website in a few weeks. I want to thank everybody for participating and wish you a great rest of the day and an upcoming weekend. Thank you.